My name is Sadie Sandifer.
I'm Chris Dobbins.
Chris Worley. And I am Jeremy Welsh.
All right, and we are going to be presenting on our research experience with Dr. Crossley. We study the catalytic hydrogen generation from methane. I gotta figure it out. Okay, perfect. So I'm going to start off talking about hydrogen energy and how it's actually produced. There's two dominant sources that we create hydrogen energy. The first one is steam methane reforming. So we take methane, we heat it up, and it's able to separate the carbon and the hydrogen. The second one is electrolysis. We're going to put it into a electrolyzer, and it's using energy to separate the hydrogen, which allows it to be converted into an energy source. In electrolysis, you can make this a renewable energy creation depending upon how you separate it, like if you use wind energy or solar energy. However, in the lab that we were working in, we use steam methane reforming specifically.
Actually that's not correct. Yeah, we were doing catalytic pyrolysis. So pyrolysis, true pyrolysis would be at a higher temperature.
Right.
And he's using a catalyst, right? So we're exploring different catalysts to turn methane into hydrogen. This is the status quo here. This is a fully developed. This is how steam reforming actually works, and then we see the pyrolysis too. But notice that steam reforming is fairly inexpensive, but we unfortunately get CO2 as a byproduct, which nobody wants, right? And so, that's actually this slide covers that. Hydrogen fuel is currently produced industrially via steam reforming, and Dr. Crossley's group is looking at some different forms of production of hydrogen.
In particular, turquoise pyrolysis.
So we're turning natural gas, and then our product is solid carbon, which are nanotubes. So we have a solid carbon source where we're able to capture some hard carbon. Okay, and then our methane is CH4, so we can get 2 hydrogen molecules with every methane molecule that we start with, right? And so in 2021, the Department of Energy launched what's a series of motivational projects where they're calling this their Earthshot initiative. And the first Earthshot that was released is the hydrogen shot, which seeks to lower the cost of clean hydrogen by 80% to $1 per kilogram produced over the next decade or so. So that would be...
That's a pretty lofty.
It is.
Very
it's a
lofty
very,
goal.
very lofty goal.
Yeah, very ambitious.
Oh, go back.
Yeah, before we go to this slide, let's go back to the reaction slide. So with steam reforming, yes, we are making more hydrogen, but notice it costs more energy, right, than with pyrolysis. So if you can bring that temperature down through catalysis, like the heat needed to get over the hump that we're going to see in the next slide, this is way more advantageous this way. So it's, even with the carbon byproducts and everything, this is the more lucrative reaction here.
There you go.
So in that previous example, like this distance here would be that 37.7 kilojoules per mole. But right now, like what we're doing in the Crossley lab is like focusing on this, right? So like brief review, like catalyst just brings that energy barrier down for that reaction, that energy cost, that activation energy. And we're working with heterogeneous catalysis. So that means that our catalyst exists in a different phase than our reactants. So our reactants are gases. Our catalyst is basically a powder. So metal like deposited on some oxide, right? So we use magnesium oxide as our support. Our metal catalyst, when we're using iron, cobalt.
Nickel.
Yes, nickel, iron, like these are metals that are pretty abundant, pretty cheap to use, right?
I think they even talked about using platinum, which is not real feasible because like it's not real common.
Yeah, yeah. And heterogeneous catalysis has been around for like over a century, right? The Haber-Bosch process for like making ammonia, nitrogen, hydrogen. I mean, that's the basis of modern agriculture.
Yeah, that's like World War I.
Yeah. The Fischer-Tropsch process for hydrogen production from syngas, so like carbon monoxide, hydrogen together, like we make gasoline and kerosene, jet fuel, things like that. Also, World War era technology. So yeah, what we want to do is we want to go from that red curve down to a blue curve. There are several ways of doing this. Most like hydrogen catalysis use a tip growth style method. So yeah, we have the metal on our support, but as we grow nanotubes, as we're converting that methane to the carbon nanotubes, like we're separating out our catalyst metal from that support. So when that reaction round is done, like our catalyst is kind of like destroyed, like used up.
Used up. Yeah.
So we're focusing on base growth techniques, right? So the catalyst stays on the support, we're growing the nanotubes, and hopefully like we can figure out how to like separate those nanotubes completely and like keep this going without gumming up that particle, that metal particle, with too much carbon to like kind of like encapsulate, to slow down that reaction.
This image right, this is actually one we grew, isn't it?
Yes, yeah, that's from,
These are actual nanotubes that we grew in some of the reactions that we did. So that's, and we'll see some more of this later on in the presentation.
and this is like like a cartoon of what our reactor looks like, right? Like we've got the,
You can see the tube, and in the tube, the gases flow through. We put the and it's kind of interesting because the tubes we use are specifically made just for this, as far as I can tell. With a little disc in the middle that we can place the catalyst on, and then flow the gases through. And over a lot of trial and error, they've had all kinds of things go wrong, and they're finally starting to figure things out, I think.
any leak in any of those lines means we can't go.
That was the first thing we always had to do, test it for leaks. And there was at one point we tested it was leaking. Try it, I don't think we ever got to stop leaking.
What the issue was, like up at the top, like you had this 90-degree bend for the pressure gauge, and that length of line just wasn't supported. So the weight of that gauge sort of like bent it a little bit. So the quartz tube, the connector up top and the connector at the bottom were sort of bowed.
Yeah.
And that compromised the connection and just constantly leaking. And he would say, like Caleb, the guys that were shadowing, okay, Fawn gets this right every single time. And it's just because like she's familiar with it, that's her system. And whenever he switched over to it, it's like, man, I have no idea what's going wrong. It just hates me.
Yeah.
And then,
And fortunately, this is at atmospheric pressure, so if you really increase the pressure, leaks would be a really big issue then.
Yes.
These reactions are done like 1 to 1.5 atmospheres. And then the pyrolysis without a catalyst is somewhere, I may be wrong, but I want to say around 1200 C.
Right, I think it's
degrees
1200.
C. So yeah, we're low. He's
You got it
lower
down to
800,
800.
800, and somewhere like that 650 and 750.
I think they've actually got production at 650.
Yeah.
Yeah.
So that's a significant decrease in temperature.
Right.
Right. The next slide has a really good image of what's going on. This isn't totally accurate in terms of our layup in the lab, but it's the same effect where we're putting in methane, there's a catalyst, and then there's two byproducts. Hydrogen, which we are going to use for energy, any form of energy. And the carbon byproduct, again, is the nanotubes, but these nanotubes can be used to make rubber. It can be used to be a second form to support different things. What else did you say that they're used for, the nanotubes?
I know he said rubber.
Yeah.
There-
Rubber is
There's
like
lots
the
of
big one.
possibilities.
Yeah.
shopping around for application for this,
Yes.
right? So part
Yeah.
of that 1-1-1 challenge is like, okay, if we're generating these nanotubes, like we can sell this like byproduct, right? Sort of like as a way to,
Yeah.
we're making revenue here.
Find a use for it.
Yeah, and we'll kind of come to this in later slides, but the gist of the issue, the potential is we have this raw carbon source. And, to sort of skip to the end, we're going to need plastics and microfibers for a long time in the future. And if we don't have to get it out of oil and natural gas, if we can take a trash gas like methane and turn that into raw carbon, then we potentially have a source to make all the polymers that we depend on for our everyday life, right? I mean, I can't walk out of the house without my polymers.
And even though we have carbon as a byproduct, this is a much safer byproduct than CO2, for example. So it's not a greenhouse gas. We can actually use it for something beneficial.
Okay, this is just some lab pictures, us preparing the catalyst, measure out the catalyst, but we have different catalysts. Like I said, we did nickel, cobalt, iron. We would mix it up in 20 milliliters of water, heat it up to remove the water, then we put it in the oven to remove all the moisture for the 20, and so you'll see it in a minute, in one of the slides, a big in bold print, we have a lot of waiting going on. We would get stuff prepared and then you just gotta wait.
And what was fun about the lab and making like catalysts is we've taken these metals and we're trying different metals because we want to see like what's the most efficient, what lowers the temperature, what creates the most carbon without blocking the movement of the gas. I was unaware, but it made these beautiful colors. And so every time like we would be mixing the catalyst, it would come out red or come out purple or it's like pretty blue. And I always enjoyed seeing the different combinations of catalysts.
I think Chris is gonna explain the different types.
I am.
Yes. Yeah, that's what I'm saying.
Oh, do you want this one or next one?
Next, there we go.
Okay, yeah, for most of the reactions, right, we're dissolving some metal salt, like some nitrate salt that's like already hydrated, right? So we want to dissolve quickly and make our solution, and we just care about that metal. We keep it warm in a water bath. This is actually just a dummy setup. Like we set this up just to take the picture. Like the stir bar isn't on. There's no thermometer in the water bath beaker. But that's pretty much what we would do. It's just weigh out our metal. And yeah, like since it's already a hydrated salt, like a lot of the times when we were weighing it out, like it's pulling moisture from the air and dissolving itself, like on the spatula, like
Yeah.
delicate microscopic materials. But anyway, we get our solution. Once that's good and dissolved, like been stirring for a while, we'd add our support, the magnesium oxide, like the powder of our catalyst. And then like we get a slurry going, transfer that over to like a ceramic bowl, crucible type bowl. Let it evaporate overnight, cover it with foil, punch some holes in there, let it breathe, and then stick it in the vacuum oven. Like pull the rest of the dissolved nitrates are still there. We want to get rid of those. Yeah, we calcine it after that. So yeah, there was a lot of just cut this for 20 minutes, wait for 20 hours.
Lots of waiting.
And unfortunately, the color went away. It went to like a tan color. All the catalysts looked the same once they were done, even though it had different combinations of metals. So that was, again, like a part of all this lab is being able to see hands-on what's going on behind the scenes, and there's a lot of things that I didn't realize were happening. Excellent.
Sure. So even though we're sort of like taking that solution, depositing metals on that support, right? Well, that support, the surface features of the support on the microscopic level, right? You've got like varied landscape, almost like hills and valleys and things like that. Not all that surface area is necessarily going to cover with our catalyst. So to sort of another method to ensure that every bit of that surface of the catalyst is covered, in fact, with catalyst is this incipient wetness impregnation. The bonus that we got this video. Is
it gonna play?
As it will, it may take us out of the slides.
Anyway, we determined like how much water it would take to like soak almost until it was wet, right? The amount of powder we had. So we prepare our solution. There's some math involved. of
A lot of
like,
it.
the exact volume of water containing the exact amount of material that we wanted to basically infuse into our powder. And yeah, we'll just play the video. You can see.
Oh,
Here we go.
Did it play?
no.
You need access.
Now I need-
Okay. Okay, anyway. We'll post that later.
It was a video.
Yeah, we're just dropping, our solution is in that burette there, and that's our powder.
Like a drop at times.
Yeah. Okay. So we also prepared thin film, basically a thin layer of our catalyst material, like on these basically silicon wafers. We've got these discs that one of the other grad students spent hours and hours
Cutting up.
cutting into these
Tiny little
squares.
squares.
And each of these squares, right? Okay, so this was on a different system. That quartz tube that we were using with Caleb had a 1-inch diameter. This one was like 1/2 inch or 1/4 inch. So we had to prepare these smaller squares, which meant a lot more cutting. Yeah, we have our catalyst slurry. This time, instead of using so much of the support, like we used cellulose as the kind of the thickener to kind of slow down the spread. Because as you see, like when we put the disc
Right here.
on there, like we detach it through vacuum,
Vacuum, yeah.
put that lid down, turn the spinner on, and then just spread out.
You can see it right here. It's not maybe hard to see, but how the catalyst is spread out on the disc.
Yeah, these wafers are silicon dioxide, and they're basically atomically thin, and so you put a spin coat it, you get really nice coverage. And then this, Chris is actually describing 3 different methods of catalyst preparation that we did here. This is the final one, and this method here actually gives us nice straight growing nanotubes that are rather consistent and
They can describe it
things
more like a
that.
forest.
Yeah.
Yeah.
Yeah,
So they're less random.
we have images of our catalyst, or of our nanotubes growing. So again, what this is doing is creating a plate where the nanotubes are just growing as that forest, as Chris was saying, instead of like just throwing the powder on the bottom of our tube and then they're growing like spaghetti. It looks like spaghetti in the pictures.
That's just more like, that's the actual reactor.
Yeah.
And you can see here, set it up, get it in the reactor, wait.
Yeah. Catalyst prep is definitely the labor-intensive portion of all these reactions.
So, you know, one of those reactions were always somewhere between 30 minutes to several hours. So,
Which is my kind of chemistry, right?
yeah, and then I think for the next several slides, it just
It's
kind of
just
pictures, images of some of the things we were working with.
This specific reactor is actually much smaller. You can see on the far corner right here is the full-size reactor, so this one's smaller. And they were using this one to study, I think, the temperature, like lowering temperatures. But this is what the general setup is. You can see all these tubes are the different movement of gases, and they're all labeled. It's very confusing. And this is us working in lab. Throughout the research, we did 2 different imaging of the nanotubes. This is TEM, which is transmission electron microscopy. And in this one, we're able to look at the nanotubes much finer. You guys want to talk about this one? So we stick our nanotubes in, and then we're able to see these beautiful images. Here's our scanning electron, and for these ones, we take the plates and we put them in. This is under high pressure, and this is what I was talking about, the spaghetti. So all those
All
lines,
that is nanotube.
that is the nanotube. Looks like spaghetti.
Now, this is just a graph of one of our reactions. You can see the blue line represents 5% cobalt, and the black line is 10%. You can see at the beginning of the reaction, the 10% is producing a lot more hydrogen. So you notice as the further the reaction goes, up to 3 hours, it starts kind of plateauing, and they're equal. And what the theory is that's going on is the catalyst is being covered by the carbon. And the surface of the catalyst, the reaction is broken because it gets covered and hindered a little bit. So we see this high reaction here, but as it gets covered with nanotubes, the reaction slows back down.
And this shows that, yeah, like increasing weight percent of our catalyst material isn't necessarily going to be beneficial, right? Like a lot of that extra cobalt isn't on the surface, it's in the bulk of the particles. We're making larger particles, and this is not conducive for the nanotube production.
And this is actually an investigation we
Yeah,
did
this is-
ourselves. Caleb helped us, of course, but this is new information that
Right.
we as a group were able to come across. So.
Yeah.
So how it's going in the Crossley lab, and well, just to sum up some notable points here. Interesting. So a lot of people did a lot of work with nanotubes up into the 80s. There haven't been a lot of papers published a lot since then, and Dr. Crossley's group has actually discovered that these catalytically grown carbon nanotubes represent a process that's reversible. So we can flow hydrogen back over these nanotubes and turn that back into methane. And so there's also there's a potential there. If we can turn it back into methane, then we can turn it into more valuable,
like
simple
ethylene.
hydrocarbons like ethylene.
Right.
You know, we're still going to need jet fuel into the future. You don't want to run your jet on solar or right for obvious reasons. So I mean, we're going to need these hydrocarbons. They're not going away. Yeah, actually, Dr. Crossley and his postdoc went to a conference in France last week, and the takeaway message from that is that this group is far ahead of everybody else in the world who's working on this issue right now. So it's pretty exciting to be a part of something like this, to spend our summers doing this, right? A lot of people are, when it comes to clean energy, right? Some people have a negative sort of take on clean energy because we're traditionally dependent upon hydrocarbons as a big source of our economic power within the state, whatever that may be. So, but the takeaway message, why this is important to Oklahoma is because methane is going to be with us for a long time. This is a trash gas that has very little value. It's what you see burning off the top of the
Landfills.
yeah, but also the processing plants. Yeah, blank there, but and so we're going to have carbon. We're going to have methane. We're going to have carbon dioxide, obviously, for a long time. So if we can turn these into other things like hydrogen with a little bit, that's great. And that also allows the existing infrastructure that we already have in the state to be used and reconverted to things that are going to power this coming age where we're going to not be as able to find these hydrocarbons out of the ground as easily as we have in the past. And that last point was just something I said earlier about, there's potential to turn these nanotubes back into raw carbon products like jet fuel and things like that.
And
That's all.
references.
Yes.
Yeah, and then we have some references and acknowledgments. So.
Thank
All right, very
you.
good.